What we're going to study today is the models of the atom. And we're going to take a look at three things. We're going to discuss the different models that exist, specifically looking at a few of them. We're going to recognize what's called the absorption spectrum for each element, which helps us identify what it is. And third, we're going to explain the atomic spectra. And that's something we're going to look at today using Bohr's model. How does it have to do with physics? So there's a whole other branch of physics called quantum physics, which is everything on a small level. Quantum means like a certain amount or like a packet. So if you ever go into quantum physics, A, you're going to obviously need to know it. And B, this is one of our like fundamental necessities to know what's actually happening with electrons and such. Okay? Look at the first model here. Now, before the Thomson model, there were just general old models. I'm going to box that off. So the old models, they existed during Newton's time. And for the most part, they were thought of as these tiny, hard, indestructible spheres. That's what people around Newton's time thought of, just this indestructible sphere. Now, that was for a long while. There were many different designs and different types, but generally, during Newton's time, that's what it was. There was nobody credited for that idea, really. Okay? In 1897, Thomson realized, well, you know what? There's some sort of electrical nature to this thing called an atom. They realized, you know what? There's some sort of electrical current that can flow through these atoms. So we have to take account for that. So we can no longer say it's just some tiny indestructible sphere. Instead, though, it's this sphere, but there's separations of charges, which allows for the electricity. And that's where this model came from. That's where it stemmed from. The idea that it's this positive. Imagine like you take, or you think about a watermelon. Okay? Everything that is red in the watermelon is a positive charge. It's this sphere of positive charge. And then you have these seeds in there. And the seeds are the electrons. That was this model. So imagine a watermelon with seeds. The watermelon is the positive charge, this sphere, or this oblate really, spheroid. Positive charge, and these negative charges represented by the seeds in the watermelon. Jack?
Yeah, didn't he, it's kind of like the watermelon. Didn't he like call it the blueberry or something?
He called it the plum pudding model.
Plum pudding.
And I realized that my grandparents knew what plum pudding was. I don't even know what plum pudding is. I've never eaten plum pudding. So I thought instead of using what the book says, plum pudding, which is the model he called it, I'm going to say watermelon seeds. It just makes it easier. It's pudding with a bunch of different, like, imagine raisins mixed into a bowl of pudding. Same idea as, this.
Are seeds in a watermelon randomly dispersed? I never know. Are they like an orange or like an apple?
Are they like in some sort of order? Are they random?
Yeah, like in an apple.
Like along the center. Because like if you get like cut it out like that, they're like
you do get like a ring sometimes of seeds in a watermelon.
Are they?
I feel like there's some like humans. Are we symmetric? No. But are we almost symmetric? Yes. I think it's like the same idea. Like you're not symmetric. Okay. Your body is not. Like you have different things on different sides of your body. But for the most part, you're like, thought of as a symmetric body vertically, right? So I don't know that answer though. It's a good question.
Yeah, I was going to say except Molly. Except Molly's
face. It's smaller than the sun.
Your what?
My eyes are different sizes.
Oh. You can't even tell until
yes,
you said
you
that.
Wait.
I've never noticed.
When I smile in pictures, it's like,
Molly's
hey!
Be nice. Next.
It's not that.
All right, the next model.
It's really not though.
The next model was the Rutherford model. In the Rutherford model, in 1911. Now, by the way, let's talk about something. Oh, actually, let me talk about the Rutherford model first. I go off on too many tangents. In the Rutherford model, the electrons are thought to orbit some positively charged central nucleus in a manner similar to planets orbiting the sun. So the same idea here, planets orbiting the sun. Now, why was this model thought of? Who remembers? Anybody remember from chemistry anything about this model? Olivier. That's right. That's exactly right. Very good. That's
the gamma ray.
Yep. Perfect. That's exactly right. So, positively charged alpha particles were fired into this gold sheet. There's a gold sheet of tin. Okay? It's called the gold foil experiment. It's a foil sheet of gold. And positive alpha charges were fired at it. Now, what the scientists noticed was this. A very small fraction of them bounced at some angle, as if it hit something. Come on, guys. Very few of them.
I thought it was gold sheet. That's what the atom was.
He said it was.
Gold sheet. Why would it be a gold sheet?
I don't know.
Gold wasn't on the dictionary.
So, listen, people. Most of these positive alpha charges pass through the gold foil. Some of them bounced at angles. And what this did was the following. And think about this for a second. What would cause a positive charge to get repelled or move away?
If there's another positive charge.
Another positive charge. So, the only thing that's going to cause this positive charge would be some other positive charge to move. If we think back to the Thomson model, that whole thing was a giant positive charge with the negatives embedded in it. So that would have caused every charge to get, or every single one of these alpha particles to get bounced off. But we noticed, or the scientists noticed, that a lot of them made it through, which meant that there was only a little positive charge out of the whole atom. And it was that nucleus in the middle. This nucleus here that I'm circling, okay, is a positive net charge, because in the nucleus you have protons and you have neutrons. Protons are positive, neutrons are neutral, giving it a positive charge. So only a few of these positive charges hit the nucleus, which enabled us to realize, oh, you know what? There's a lot of empty space in here where they can pass right through. Only when it hits the nucleus does it go off at an angle. So that's where this model came from, the gold foil experiment. Now, unfortunately, one thing that it also caused was the idea that the atom seems to be unstable. Why would somebody think this model is unstable? What does unstable mean?
Press the goddamn button.
What does unstable mean next time?
Sorry.
Paul.
You don't know where the electrons will be.
Yeah, it has some sort of random movement, or it could explode at any time. Or an unstable building could what? Fall and collapse. So there's some sort of collapse or explosion of something that is unstable. Now, why would this model be thought of as unstable? Why would this model be thought of as unstable? Let me give you a little hint. Oh, Stash, go ahead. What do you got?
Because the light particles travel through at random. What's the question?
Why would this model, with electrons orbiting a centrally charged nucleus that's positive, be considered unstable? Why might it be considered to either collapse or explode? So what happens when there's all this positive charge and all these other negative charges? What do the negative charges want to do, Masha? Yeah, or like go toward the positive. What is that? Why does that happen? What do we learn about?
Opposites attract.
Yes, there it is. Opposites attract. So theoretically right now, these electrons are in orbit about to crash into the nucleus, right? They're about to spiral into the nucleus because they're opposite charges. They're going to attract. But for some reason, they're not. And that was the problem with this model. We realized that this model predicts an unstable nature of the atom, yet we know that the atom exists in a stable state. Only unstable when we cause it to be, like a nuclear reaction or fission. Okay? Now, that means that there must be something else missing. So, as a result of that, what scientists decided to do was say, let's test a little bit more. Let's keep on testing now. So they looked and they said, let's run experiments. And this one experiment was one that really helped them understand what was going on. And this one experiment, here's what happened. There was some sort of voltage or potential difference that was applied across gases in a tube. Okay, and this was an experiment that was not necessarily one that they said, oh, this is definitely our experiment that's going to make it work, we're going to know everything from this. No, they had no idea. But discoveries work that way. You don't always know, right, what's going to be discovered. So, they had these gases in these glass tubes, and when there was a voltage applied to them, they were able to conduct a current. And each of these gases gave off a completely different color. So yeah, they might have been shades of blue or shades of red, but no two gases gave off the same color, which was pretty crazy to think about. And these gases were they were in their atomic form, which means it was like all helium gas, or all hydrogen gas, or all neon, or all argon, etc., etc. So what they noticed was that the gas, its color, indicated the element that was present in the gas, which was pretty interesting to think about. It was a way of identifying what was in a component of gas. So like around you right now, there's argon, there's nitrogen, there's oxygen, there's carbon dioxide, which is a mix, obviously. Okay, there's some methane. There's a lot of different gases in the air around you, and if you wanted to figure out what it comprised itself of, you could use this method. Now, there's a lot more into it than just this now, but the idea is there. So, what they were able to do was the following. Okay, what they were able to do was the following. They noticed that when the gas was passed through a prism, okay, so the gas comes in right here. Here's the actual light from the gas. The light gets passed through this slit, which concentrates the light. That light gets passed into the prism. The prism then breaks up to the light into its components. Remember, white light gets broken into all the colors. But if you start passing light through a prism that is red, it's not going to break up into all the colors. So you started getting different spectrums of colors that showed up on this viewing screen. Not all of them, but only parts of them. So for example, hydrogen has this like violet, dark blue, light blue, and orange. Helium has dark blue, light blue, teal, yellow, orange, magenta. Okay, it's got a bunch of colors. And what was noticed was that depending on the element, there was a different spectrum. So it was like an identifier. Imagine being able to say, you know what? We could figure out exactly what this is just from doing that. What did this lead them into doing? This led them into discovering new elements, because they would get new spectrum that they'd never had before. They'd get these different spectra and they'd say, oh, this has got to be a new element. Let's figure out what it is. And that's really how helium was discovered. That's how helium was discovered. Okay? And because they realized that the sun produced this same spectra, they realized that the sun must be made mainly of helium. And they called it helium because the sun was called Helios in Greek, and therefore the name for that gas became helium because it was from the sun. Okay? But these are ways that discoveries were made. Now, does that make sense so far as an identifier is being used? Okay, you can identify what's going on. Now, what I want to talk about next is called the Bohr model. The Bohr model. And the Bohr model came as a result of the atomic spectra that we just talked about. And in 1913, Bohr said the following. Bohr said something that to me was not very boring.
Oh my God! He totally said it.
He said that electrons.
What is this guy did?
Electrons are found orbiting. They're found orbiting the nucleus still, but they can jump from one orbit level to another, and that was the big difference. Okay, they could jump from one level to another, and here's why it's not. Yes, it's not boring. It's very interesting. Here's why. First,
It's more interesting.
this led us to realize that each atom was differently spaced. The elements. So, for example, helium has 2 electrons, and they were orbiting in this one ring. Whereas in the next, say, orbital shell or shell of electrons, you would have elements like carbon, which is like carbon's number 6 or 8. Which one is carbon?
6. Carbon 6. Carbon 6.
C6, yeah. So carbon has 6 electrons, so there's 2 electrons in the first shell, and then 4 in the next shell. So we started realizing that the actual elements themselves looked different. Okay, they look different. Max. Now, what this led us to understand was this. The electrons would give off energy at times. and the atoms as a whole would give off light. And we're going to talk about something called photons in a minute, but they would give off energy. And what we noticed was the following. The energy that it gave off was a result of the electrons moving levels. And that move in level, or that change in level, changed its potential energy, or it gave off some sort of energy. So have you ever gone to see the Northern Lights before? Has anyone seen the Northern Lights?
Yes, I always wanted to.
Leave it, Garrett. Has anyone seen the Northern Lights?
Yes.
Okay. Do you want to describe it for us? Do you remember what it looked like? What Northern Lights looked like? Fine. Let's just see it again, Max.
Well, yeah, I've seen it in the sky because it's something like it's the way it's like the atmosphere in that place, or like the way it's all these gases. There's something. It's the.
How often does it happen?
Max,
really
it's such a
we really see like in the North Pole because that's like the see your wallpaper.
So he's on the right track, guys. He's on the right track. It has to do with the atmosphere around there. Okay. What's up?
Why they see the northern lights? Oh, when the sun.
People, stop talking. Listen.
When the sun releases, these like solar flares, it goes, it hits the magnetic field of the planet, and since like the poles are where like they end up,
Concentrated.
they are concentrated. And since if you're like north enough, you'll be in sort of that area where like the poles end up. So if you're like in Iceland or like Norway or even higher up in like Canada, you can see them. It's like when the sun like is it's like between like I don't know like 10 below and 0 below, or 10 and 0 Celsius. You can see it. I'm not sure why, but
That's the general idea of what Olivier said. There's a little more of it that we're going to talk about today, so this might answer some of those questions. So we're going to go into a little more detail, more depth. But the idea is right. There's this magnetic field that is causing it. Okay? And we're going to talk about how it has to do with photons and energy levels today. Okay? Now, the third thing you want to write down here, so again, okay, we said that the electron radiates or gives off energy when it jumps from some orbit to another. The third thing I want to talk about is the frequency of that radiation. Okay, and the frequency of that radiation was noticed to follow this equation, and it was discovered by a guy named Max Planck. And the equation is called Planck's equation, and it says the following: E equals h omega. Okay, E is the change in energy. H omega. Remember that symbol for frequency? H is, yes, Planck's constant. And omega is the frequency. No. We'll get to E equals mc squared this year, but not right now. We will. Now.
They just saw it for the first time.
What are the units of energy? People, come on, focus. Good, Jeff. Walking in and answering right away. Nice. Energy is joules. Anybody remember frequency? This is a tougher one. Frequency. Very good, Tyson. Hertz. Hertz. And Max for Max Planck. What do you think the units of Planck's constant might be?
There's no units.
Well, there's got to be, because the joules and the hertz have to balance.
Joules per hertz.
Yeah, and now a hertz is 1/2. So this is really units of joules per hertz. But we're going to write it, instead of like that, we're going to write it as joules times seconds. Because hertz is 1/seconds. Remember, hertz is 1/seconds. So if you put a 1/seconds in for hertz, it bumps up to the numerator. Okay? So again, this is the equation that we're going to be using in this section. Now, before we get into any mathematical part, we need to look at the idea of electrons jumping from one energy level to another and why they do that. And why they do that. Okay, to do so, what we're going to do is we're going to talk about a topic now called spontaneous emission. Okay? Spontaneous emission. So, first, let's define the term photon. photon is 1 unit or quantum of light energy. So when the sun lights up the day or lights up the world around you during the day, those photons are units of light energy. Okay, and that's what enables you to see, the photons. Now, if a photon interacts with an electron, okay, it can cause it to become what's called from a stable state to an excited state. Stable to excited. Now, that's what's happening right here. So this electron is on its normal orbit, the inner shell. It gets hit by a photon which has energy, which causes it to jump to the next level, which is called the excited state. But the excited state is also called the unstable state. It wants to go back to its original place. And when it returns to its original place, it emits energy. So it's like it's absorbing the light, okay? And then it's giving off the light. It's absorbing the light, and then it's giving off the light. So what's happening here is, depending on the amount of a jump it takes, a different light wave of frequency is given off. So remember earlier we talked about those atomic spectra, where certain elements or certain atoms give off certain colors. The reason they give off different colors is because when it runs a voltage, when a voltage was passed through those gases, the electrons were jumping. And they were jumping from different shells to different shells, which gave off the different colors, which is why the gases were all different colors. Now, the idea, though, is that the amount of energy that the photon has to match the amount of energy that it takes to make this jump right here. So imagine that energy level 1 and energy level 2 are given. So let's say, and this is not a math problem, I just want to give you an example. Energy level 1, let's say energy level 1 is 6 electron volts, and I'll talk about what that means, an electron volt. And energy level 2 is 3.5 electron volts. An electron volt is a type of energy like a joule, but a very small joule. And we've defined it because it's such a small amount of energy. So let's say that electron level 1 is 6 electron volts and energy level 2 is 3.5. What that means is, for an electron to get bumped into second level like it did in this diagram here, what's the difference between these numbers?
3.5.
What is it?
No, 2.5.
2.5, right? So what that means is that for this electron to go from energy level 1 to energy level 2, it needs to be hit by a photon with exactly 2.5 electron volts of energy. So those photons are not all going to cause the electrons to move, only the ones that have the right amount of energy. So it has to match up with it. Okay? Yeah, let's shut the air off. It is getting very chilly. Thank you. Now, once you can take your blazer off. Once it is in an excited state, okay, it's going to want to jump back down, causing this photon to be emitted. What's happening in the northern lights, okay, is that the photons, this is where the northern lights really work. The photons get trapped. So as Olivier said, the sun's rays, the photons from the sun, are getting trapped in a magnetic field. And what they do is they end up interacting with this gas the same way the voltage interacted with the gas when it passed through the gas chamber, or the gas glass chamber that was there. So you have this chamber of gas that's contained, that we talked about earlier, and it applies this potential difference across it. The color that's given off is analogous, guys focus, is analogous to the northern lights. Okay, to the northern lights. Now, one thing that you should know, you should write down is a constant, and I'm going to put this on your formula sheet, but you should write it down, is 1 electron volt. 1 electron volt is the equivalent of... Go ahead. I heard it, go ahead. What's the units? Joules. Shh, guys, stop. 1 electron volt is defined as, look how many joules that is. That's a very small amount of joules. Instead of writing down this tiny amount of joules over and over again, scientists defined the electron volt. And they said, well, you know what? The electron volt is a much smaller unit. It's like saying this. Please, honestly, right? Think about this for a second. Would you ever say that an atom is 0.0000001 kilometers in length? No, you would say it's like 1 nanometer or 1 millimeter, right? You wouldn't use a kilometer to describe an atom. So you wouldn't use a joule to describe the energy given off when electrons move because it's so small. So you use the electron volt instead. Okay? Let's take a look at an example for today and then we'll be finished. One example for today. A photon in a mercury atom drops from energy level 4 to energy level 2. It drops from energy level 4 to energy level 2. By the way, I don't know if I wrote it backwards in the example. I apologize if I did. A minute ago I gave you examples of energy levels. The higher the energy level, like level 4, the higher the amount of electron volts.
Yeah.
So I think I might have switched it. Did I look at your last notes?
Yeah, you did.
Somebody look at the numbers real quick.
You did.
Yeah, switch your numbers, please. E1 should say 3.5, and E2 should say 6. So switch those, please. Now, if 1 electron volt is equivalent to 1.6 times 10 to the negative 19 joules, then determine the frequency, the frequency of the photon emitted. If the frequency is in that little band of frequencies that describe visible light, we'll see light. If not, it'll come off as like infrared or gamma radiation or a microwave. So we have to go back and think about our frequency table that we looked at earlier in the year. Let's write down our givens. Energy level it starts at is, where are we at? From level 4, so 5.43 electron volts. Energy level 2 is 4.66 electron volts. Let's subtract these first to get our change in energy, and then we'll convert it to joules. Agreed? Subtract these to get the delta. What do we get for delta in this problem, people? The change in energy.
It's like 0.077.
What is it?
0.77. No. Yeah, no. That's
77 or something. 67?
Are you just subtracting the two, EV1 and EV2?
77.
We could all either do it in our head or use a calculator, but we need to verify. Thank you. But I want to see you actually doing it, guys. So really, take out your calculator. Again, I'll say it. Thank you. Now, that's the change in energy. And remember this formula. What's the frequency represented by? Which variable in this formula? What is the frequency represented? Which variable in this formula? Omega, yeah. The W looking symbol, right? Yeah. So we're trying to find the frequency. So let's divide by H. So we have the value of E, but that value is in electron volts. So we'll convert that. What's the value of H? How are you going to find out the value of H?
It's 1.6.
But I think you said always put the less one on top.
How are we going to figure out the value of H?
It's 1 over seconds. Does that mean anything?
Right? We have the energy change. We just solved for it.
Oh, it's a constant.
H is a constant. Thank you. People, you got to pay attention and answer questions. Come on. H is a constant. We said that like 30 seconds ago. It's the Planck's constant. Now, so we have to take this 0.77 electron volts divided by H. Planck's constant was given as 6.63 times 10 to the negative 34, and the units were joules times seconds. That's Planck's constant. And the unit of energy is, it's 0.77 electron volts. But we can't have electron volts because look at the denominator. What kind of energy do we have in the denominator? We have joules, right? So we can't leave that as electron volts. So we have to multiply. Electron volts are on the top. How do I get rid of them? Put them on the So what's the joule unit on top? What's the conversion going to be? What did I tell you a minute ago? Conversion between electron volts and joules.
1.6 times 10 to the negative 19.
Joules, right? Equals 1 electron volt.
So let's multiply that.
Okay, just to section that off. I should have wrote a little lower. So yeah, our energy that we figured out, our change, was given in electron volts, but we want it in joules. So canceling these units now, we see that we have it in joules. And we'll get a value. Okay, we'll get a value for omega. What does that value turn out to be? Raise your hand. Raise your hand, Jeff.
1.232 times 10 to the negative 19.
I got a different value.
You mean up for the top part?
The whole thing, the whole answer. Sorry.
1.85, 8, and then I got a long number, and then it's 10 to the negative 35.
To the...
Would you get 35? I got.
I didn't get negative 35.
I got 14.
I got 14. Take a look, people. The joules cancel. We get units of 1 over seconds. But 1 over seconds is just hertz, as we said before. Okay, 1 over seconds, that was here, is really just hertz. Now, if you didn't get that, you need to A, figure out on your own how to do it, or B, come see me. One or the other, please. Don't continue to make mistakes on a calculator for silly reasons. Now, what you'll notice is if you go back to when we studied radio waves and we looked at frequency and wavelength, we had a table. And it started with like microwaves, it went to visible light, we looked at infrared waves, looked at ultraviolet, we looked at gamma. This wave turns out to be an infrared wave.
How do you know that?
Because I looked it up. I just looked in the table, guys. You have the table in your notes and in your textbook. It turns out to be, infrared wave. Now, had this frequency been a little bit higher, remember, infrared means below red. Infra means right below it. Ultra means above violet. So ultra is above violet, infrared is below red. If it had been a little higher, okay, it would have been a color, like red, or orange, or yellow, or blue, or green, or indigo, or violet, or one of those colors, okay? Now, it happens to not be, so it turns out to be an infrared wave. Okay? Infrared wave. Any questions on this one? Okay, those colors you're seeing, Aurora Borealis, I think is the real name, or Northern Lights, whatever it is the different colors of the spectrum. Okay, that's what you're actually seeing there. Practice these questions, okay? There's an interesting read on page 846. And then on page 847, numbers 1 and 2 and 4. Yeah, Jeff?